I'm happy to be here, and I'd like to begin my presentation by thanking Matt and Emily for inviting me, and thanks to all of you guys for being here. My name is Surendra Akhikari. I work at NASA Jet Propulsion Laboratory in California. And in this presentation, I'm going to demonstrate the power of a single station bedrock GPS to constrain the dynamic mass transport through a neighboring glacier. The glacier that we will be talking about is Ring Glacier, as you can see here. Very nice picture provided by Operation Ice Bridge. The ice flows into the ocean, so here is the fjord. And the GPS station that we will be utilizing to constrain dynamic mass transport that travel through this glacier is located on the rock outcrop somewhere up here. And before we go into further details, I'd like to acknowledge contributions from my co-authors, Eric Ivins and Eric Larue. Both are also from JPL. Okay, let's get started with a brief background. There are more than 50 GPS stations that are planted on the bedrock around the periphery of the Greenland ice sheet. The background map here is basically the major ice surface velocities to highlight the location of the GPS stations relative to the fast discharge glaciers, which are shown in purple here. So the measurements provided by these GPS stations are used for many applications, for example, to weigh the contemporary mass loss from the ice sheet, and also to quantify the ongoing rate of glacial hydrostatic adjustment. These and many other applications mostly rely upon the measurements of the vertical crustal motion. The horizontal components have not been fully exploited partly because horizontal displacement have a relatively muted amplitude compared to the vertical counterpart, and also because these are considered to be a bit trickier to interpret. So in our analysis, as we aim at utilizing all three components of the GPS measurements, it is instructive to look at the theoretical sensitivity gradient maps. So basically here, what we see, basically these maps are adapted for the ring station, which I saw in here. So ring station right here and here. And so basically these maps show how sensitive the measurements, the GPS measurements at this particular station is relative to the applied surface load. So basically du over dh, h being the surface load. The map in the middle is for the vertical component, U1, and here is for the north-south component of the horizontal displacement vector. And units here reflect the fact that, it reflects basically a measure of how many micrometer of displacement is recorded at this station, which is again here, when we apply a 1 meter ice load per square kilometer area located anywhere inside the domain. So clearly we can see the negative gradients associated with the vertical component. So what that means is that if we apply some load anywhere in this domain, the station is always going to record subsidence. This is fairly intuitive. But if we look at the horizontal gradient maps here, we can clearly see a dipole. You see the values go from minus something to plus something. So what that means is that if there is a reasonable symmetry in the distribution of load about the GPS station is always going to record negligible or very muted horizontal signal. So in other words, what that means is that in order to get the detectable amount of horizontal motion in first place, there must be some sort of asymmetry in the spatial distribution of mass anomaly. And this asymmetry in the present context arises from glaciers. And this is the key idea to our GPS data interpretation. So we investigated all of the GPS measurements at those 50+ stations very carefully and found pretty interesting signals at Ring Station. So Ring Station is located on the rock outcrop adjacent to the Ring Glacier, which is one of the major outlet glaciers in the western Greenland, right here. And here I saw the GPS measurements, all three components of them, vertical component, north, south, and east-west components, after removing the train and acceleration terms, so that these signals can be attributed to climate-related seasonal variability in the surface mass. And indeed, we can see a pretty nice and smooth seasonal pattern associated with the vertical component, and which is not really showing up in the horizontal data. But when we plot the horizontal components of the displacement vector on a map view, something interesting emerges. And here it is. So here, what I saw is northing versus easting. So basically, what we see here is the trajectory of the GPS station on the horizontal plane. So in red, I highlight the trajectory of the bedrock in year 2012. And so from the beginning of June 2012, the bedrock was moving to the northeast by more than about 12 millimeter over the course of 4 months. And then the bedrock returned back in the following several months. So this is a very substantial and systematic motion of the bedrock. And similar pattern was also recorded in year 2010, which I saw in blue. Again, it goes up and comes down. And nothing systematic, nothing really happens in the rest of the years. So one thing that I'd like to remind all of you is that 2012 has by far been the most intense melt year for Greenland ice sheet. In fact, for a couple of days in mid-July 2012, the surface of the entire ice sheet was melting. So the question that we ask ourselves is that what should be the driving mechanism for the substantial and systematic motion, the horizontal motion of the bedrock, by using a simple crustal displacement model? And to this end, we rely upon JPL's ice sheet system model. So ISSM is basically a system model that can calculate high-order physics of ice flow, and at the same time, it can also compute a whole suite of geodetic parameters or geodetic observables on a global scale, including what we call the sea level fingerprint, and also the crustal displacement, which is the most relevant observables for this particular purpose. And we basically rely upon this radially symmetric standard preliminary reference Earth model to parameterize the solid Earth. And we compute the Green's function and convolve those with the surface load on an unstructured mesh, as you can see, for example, in here. And this truly allows us to capture a kilometer scale feature, such as mass loss from small glaciers, while also accounting for this global loading problem. And so we are continuously developing this capability. So now the version 2 that we are about to submit soon can also compute the displacement and stress field not only on the surface, but also at a given depth. And of course, induced by both surface loading and also tidal forcing. And we can also have this solid Earth structure. We can vary the properties of the internal structure by simply tuning the material properties or the layer thickness. And so all of these features will be highlighted in our upcoming ISSM Sea Level workshop in June. That will happen right after AOGS annual meeting in the University of Hawaii. Okay, let me get back to the main topic of the presentation, which is essentially to model the measured horizontal displacement at Ring Station. At the first modeling exercise, we force our global crustal displacement model, deformation model, by a global surface load. And for that, we rely upon the GRACE and complementary data product. So GRACE, which unfortunately is no longer in operation, has provided us with a pristine set of data of the mass transport between the land and the ocean as we, okay, it's not playing. I have animation here, but for whatever reason, it's not playing. Anyway, so this is not the main thing anyway. So the whole point here is that, so GRACE provides us at a monthly time interval the global coverage of the mass distribution between the land and ocean. And we can also use the weather model-based complementary data products to account for the non-tidal mass transport between the atmosphere and land and ocean. And I had a pretty nice animation for that over here. So anyway, so we force our global model by these data set. So by the way, when we combine these two data sets, then we are essentially forming a robust model of mass transport, climate-related mass transport on the surface of our planet. Okay, so we force our model by this data set and retrieve the three-dimensional predicted crustal motion at ring station, and here is what we find. So in black, in the background, are the observed data that I showed you before, and the red lines here are our model reconstruction that came from the grace forcing. And we can see a pretty nice match between the observation and model simulation for the vertical component, but for horizontal, that is not the case. If we really want to quantify, how much grace can explain the horizontal crustal displacement, so let's just focus on the most interesting signal which happened in 2012. And for the 4 months in summer, from June through September, the measured data shows that the GPS was heading this way by about this particular rate. And during the return time period, so that's the rate of the bed motion. And in green, what I plot here is basically the quantification of how much grace can explain in terms of predicting the horizontal displacement there. But anyway, in summary, so grace can nicely explain the vertical component, but it cannot say anything about the horizontal displacement. And we know why. If you recall the gradient maps that I showed in one of my earlier slides, the reason is that grace simply does not have a high enough spatial resolution that is essential to capture the local asymmetry in mass anomaly, and which is essential to induce the large amount of displacement as, such as the ones recorded by ring station. And so next logical step that we take is we maintain this global model of crustal deformation, and we simply refine the spatial distribution of mass within a local region. And we define this local region to be the grace mass cone, as you see in here, that encompasses the ring station. And within this local domain, so now we use a physically based surface mass balance model. So these models are primarily driven by the regional climatology, and they take into account many climate-related mass parameters such as rainfall or snowfall, evaporation, melting, and runoff, and so on. And we use 2 state-of-the-art mass balance models, MAR and RACMO they are called, and then we retrieve the largest predictions out of these 2 models, and here they are. So again, red are the observed data, and in blue, I saw the predicted horizontal displacement forced by this global load that encompasses the high-resolution mass distribution that comes from MAR and RACMO models. And again, you cannot see animation here. Anyway, so but one caveat associated with these 2 models that I should highlight here is that these models essentially assume a kind of instantaneous routing of the meltwater, whereas in reality, a portion of meltwater that is produced is likely to get retained locally. So what that means is that, so these estimates, in my opinion, represent the higher end of estimates. In any case, SMB can explain a part of the signal, but it cannot explain, it cannot be the major driver of the signal. So I'm fairly confident about that. And then we did a bit of research to see whether there were any anomalous kind of catastrophic events such as earthquakes or big calving event happening in 2012, and we did not find any such evidence. So taking all things together, so by the process of simple or standard elimination process, so we are compelled to look for a coherent pattern of mass transport passing through the neighboring glacier, which happens to be Ring Glacier. And now everything becomes much simpler. Okay, so here again, I saw that sensitivity maps. So I have rotated this map so that we could explain this mean displacement vector during the 4 summer months here. And the idea here is that, so again, you see the dipole here, and the white essentially shows the margin of the glacier, Again, glacier flows this way, and this is the field, and the GPS station is shown by a black dot. So based on this map, what we can tell is that in order for us to be able to explain this vector of GPS motion, we are left with three options. The option one would be there must be a lot of mass being lost from this blue area, and we presume it should be confined within the glacier area, so that is our assumption. And the second option would be there should be alternatively a lot of mass accumulation that should happen in the red area. And the third option, of course, would be a combination of two. Again, recall the fact that we are dealing with the summertime of the most intense melt year that Greenland has ever experienced. The choice becomes obvious, and it is that we assume or we believe there must be a lot of mass being lost from within the glacier. Okay, so now, so now we can fairly straightforwardly calculate how much mass must be lost to explain this observed mean monthly displacement vector. And this, again, you don't see the number here, but the number would show something about 1.7 gigaton per month. So that is the number, I mean, that is the amount of mass that must be lost from the trunk of the glacier to both satisfy the direction and the amplitude of the observed displacement vector. And in red dot here, inside the glacier, what I saw is what we call the centroid of the mass anomaly. And so this must be maintained in order to predict, the observed direction of the crustal displacement. And our inference of ice thinning, again, which is equivalent to 1.7 gigaton per month, is consistent from glaciological perspective, from glacier mechanics perspective, because we know that whenever we have a large melting happening on the surface, it can either enhance the basal sliding, or it can also soften the shear margins between the ice and the adjacent bedrock, and hence causing the glacier to draw down dynamically. So this is a fairly well understood or fairly well explained mechanism of fast discharge of the glaciers. So we play the same game for the returning time period, and so instead of mass loss that is shown in blue here, we now gain mass in the trunk in the following month. So that would start from the beginning of October all the way through to the mid-January 2013. And our interpretation is that the routing of meltwater that was produced in the far inland of the ice sheet is expected to be delayed and inefficient. And whenever we have inefficient drainage system, that is expected to cause a large-scale sliding, and thus transporting mass from the far inland of the ice sheet down to the trunk of the glacier. So, this interpretation is consistent with the independent measurements of the velocities somewhere just around here that would show the sustained increase in velocity that goes well into the mid-winter in 2013. And the number we had here, if I recall correctly, would be on the order of 0.8 gigaton, roughly half of what we have in here. And so again, so you can do we can play the same game for every single month of the displacement vector. As you see here, from June, July, August, and September in black. So you could see how the bedrock has been just shifting, and the direction is showing kind of the clockwise, nice and clockwise behavior. And then we can literally compute the corresponding mass anomaly that must be lost from this portion of the glacier. And again, those circles show the centroid of the mass, and relative size is meant to highlight the amount of mass being lost on that particular month. And just by simply tracking those mass centroids, we can even quantify the speed of this, what we call this wave-like pattern of mass loss. And again, this number here should be on the order of 7 kilometers per month. And remember the fact that, so this is one of the fast flowing of the glaciers with typical speed of on the order of a couple of kilometers per year. And here we are talking about 7 kilometers per month for at least for 4 months. Okay, and I don't recall that number here anyway. So, And if we want to be a bit, I mean, the same information can be presented in a hopefully more appealing way. And what I saw here basically is, so this is the GPS station, and so glacier flows this direction from up here to down there, and the point, arrow points basically the direction of the bedrock motion. And what you see as the mass is being transported down glacier, and the behavior of GPS station in terms of its horizontal displacement is depicted by these arrows. Okay, so now let me quickly wrap up what I had just said. This wave-like pattern of mass transport that we have detected using a single station GPS data, to our knowledge, it has not been, or is kind of the first of its kind to have ever recorded for any of Greenland or Antarctic glaciers. And we quantified that the mass in motion that is involved is such that at a minimum of 6.5 gigaton of ice must have been dumped into the ocean over the course of 4 summer months in 2012. So by the way, one fact that I like to highlight here is that because we are relying upon a single station measurements of GPS, we cannot really justify using a high order, full-blown ice mechanics model to replicate some of those observations. And also a word of caution is that this is by no means a formal inversion of mass loss. This is a simple inference of mass loss based on the single station data. Anyway, so we quantified about 6.5 gigaton of mass being dumped to the ocean, and that accounts for the 50% increase in the mean annual discharge rate for this glacier, which is on the order of 10 to 12 gigaton per year. And so we do not fully understand the whole chain of processes that would that cause this wave-like pattern of mass transport. But one thing we are sure about is that this must have been triggered by the intense surface melting. And if so, we are more likely to witness this kind of phenomenon in the future more frequently, simply because in an ongoing climate warming, we expect early onset of melting, early onset of summer, more intense summer melting, as well as the inland propagation of melt areas. And this will have some ramifications for future sea level rise. And just a final few words from geodesy perspective. I think it is important to recognize here that we have just utilized a single station GPS data to tell so much about what we can do in terms of constraining mass through a important glacier in Greenland. And imagine that if we have an efficiently engineered network of GPS stations, for example, a couple of stations on either side of the trunk of the fast discharge glaciers all around the Greenland, and when we combine these kind of measurements with say, space-based observations to be provided, for example, hopefully by the future NICER mission, then I believe that we can truly revolutionize the way how we constrain mass in the contemporary dynamic ice sheet models. So I see a great opportunity here, both for ice sheet physicists like us, and also for geodesists or GPS people like many of us, I'd say. Okay, so I stop here. Thank you.
We have a few minutes for questions. This is being filmed, so if you can go to the microphones to ask your questions.
Nice presentation. I was just wanted to ask, you're looking, your interpretation in terms of the dynamics, what does that imply for the surface kinematics of the glacial ice? And are there any data to support that?
Yeah, this is a great question. So if the dark blue in here basically shows the thinning of ice. So, and if I recall correctly again, because I don't have number here, the thinning rate that we infer would be on the order of 7 to 8 meters per month. So if you accumulate that number over the time period of those 4 months from June through September, that would be roughly about 30 meters. So what we are saying here is that the glacier must have been going down in terms of its surface elevation by about 30 meters. And we tried to see that signal, for example, using the Cryosphere-based measurements of the elevation change, and we could not find anything that could support or even, oppose our hypothesis. And for example, what I saw here is work from one of my friends from JPL, Johan Nilsson, and so what we see here is from January of 2012, February, and so on, the change in surface elevation in 2012. And as you see here, the data are really fuzzy, and we cannot say anything about whether we can, detect that kind of drawdown that we have been inferring. So yeah, I'd be open to talk to any of you guys if you have some other independent set of data that could either, either explain or even defy what we are saying here. Thank you.
So recently there was a JGR paper, they use a global distributed GPS network, and they discover actually the disagreement between GPS measured horizontal deformation and Greece model deformation is mainly due to geocenter motion. So did you consider that effect in your model, and what's your opinion about that? Thank you.
Well, yeah, this is a great question. And so as far as I know, both the data set that we use and the model that we have both operate on this center of geometric center of so which is consistent in that respect. And yeah, I think that's all what I can tell. So as far as I know, there is no inconsistency associated with this geocentric motion in our analysis.
Any more questions? I'll ask one quick question. Is RINC special? There are 50 GPS around Greenland. Did you only see it at RINC, or is it around the continent?
Sure, yeah, that's a great question, man, thanks. We actually looked at, all of those 50-plus stations very carefully, and certainly there are many interesting signals recorded by many of the GPS stations. And let me quickly show some of those, maybe. So you see, I don't remember the names, maybe you might, but you see one station right here, and you see a network of glaciers. And another station here, fjord and glaciers are far away. The scale is about 5 miles, right? And you see pretty beautiful pattern of the crustal displacement. And these are pretty a large amplitude. You could see 10 millimeter into end, right? The whole point is that, so as we want to interpret these signals, then we want to choose a location where we can infer with less ambiguity. For example, here, so just based on this data, we would not know how to distribute mass uniformly between here, 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 and here, because each will have their unique signature in terms of directionality, right? And in here, I think glaciers are too far. If you recall that gradient map that I showed, and this is 5 miles. I don't know, but I think this is definitely too far from the station to say something conclusively about, okay, so this signal we witness here, which is that signal, is due to this glacier or this glacier. So yeah, that's a good question there.
Great, thank you.
Thank you.